looking at what happens when a long, slender, the axial dimension being the greater one on these type of members, and we're loading it in some kind of torsion or twist. And we found out the other day that the maximum shear stress then will be, of course, a function of the torsional load. This is the applied load, just like the axial force was before. Also a function of C over J. Remember what those two things are? What's C stand for? And it's true now, and it's going to be true for the rest of the term that we use this C in this way. So it's very useful that you recognize it.
The maximum radius.
It's the maximum rate. Well, right now it's radius, but we'll be looking at non-circular cross sections in a little bit, and so it could be the maximum distance. For example, we could look at T-beams, and we're going to find what's called the neutral axis, and then C is going to be the greatest distance from that, which could be either up to that edge or down to that edge, depending upon the geometry of the cross section and where this neutral axis falls. But it does mean the maximum distance from some neutral spot. And for circular things, of course, a neutral spot right at the center makes some good sense. So it is the radius for these circular cross sections. We're not actually going to do it, but if you want to just read through one of the chapter sections we're skipping, it discusses, I believe, non-circular torsional loads on non-circular members, also on what are called thin wall members, which is any very, very thin walled tube of some kind. So that will stand for the maximum distance for the next couple weeks for lots of the things we look through, whether they're circular or not. And remember what the J is? Oh, no, why not? J. I mean, if nothing else, go by the first letter and see what it stands for, because that always works. Phil, you remember?
I know it doesn't start with J.
My favorite student comes to the rescue. That's the polar moment of inertia. It's just like our regular moment of inertia that we had. We looked at a lot in statics last term, only for circular shapes, circular cross sections in this case. The intermediate equivalent of that, of course, this is just the maximum load, but that's where most of the concern is. We can also look at some intermediate radius, some radius where we're inside the piece, but that's not quite the concern, certainly not on solid pieces, because the maximum stress is at the outer surface. But it could be, if we have a tubular cross-section, you could be worried about the stress at the inside where maybe there's cladding or adhesive or something similar to that. All right, so we're going to add to this a little bit now as we do just what we did in our axial loading, where first we looked at the loading and its direct effects in terms of the stress induced in the material. Then we looked at the deformation under those loads, which is really the step we took beyond what we could have done in statics. We could have done the internal stresses in statics and not gotten out of the general purview of that subject. But adding the actual deformation of the pieces. And we're going to do that now, look at the deformation of some piece when loaded by some torsional load, as would happen in a drive shaft. So if we put a couple reference lines down here, so imagine down the parallel to the axis, but inscribed on the outside, maybe not a real inscription, but just for a reference point of view, and then one from there down to the radius, and see what happens to that under this torsional load. As applied like that, we expect that this front face here would turn in some measure, greatly exaggerated there, and that the line inscribed on the outside would also have some angle to it. So again, the deformation caused by the loading, greatly exaggerated here just so we can see it, but would look something like that. So let's put a little bit to this. Let's imagine this is of some length dx. We have an angle here that we have already investigated. That happens to be, of course, the shear strain. Remember, that's the deviation from an original angle of 90 degrees. And if you want to look at it from some side that maybe if I draw it on edge, this reference line that was like that and now deforms to that because of the torsional load, this is indeed the strain, because we can look at this angle here as the original 90-degree angle that's now been deformed, and the deformation of that 90-degree angle is our strain. So we've seen that before. I don't remember if we've seen it in exactly this way. And then this angle on the end here, we'll call that some amount of deformation, d phi. And then this arc length subtended right there, if that's the right word, is the shear strain times that distance over which it acts. That's the arc length from the axial direction, and from the end-on direction, then of course we've got the equivalent arc length c d phi there. Or the shear strain is some geometric constant of the geometry of the cross-section over d phi dx, and then we're almost ready to integrate that. Remember that we've got this material constant we call the modulus of rigidity, which is the normal stress over the shear stress. So we can put that in, and we get then, combining those two, we get that the maximum shear stress is equal to two constants, the product of two constants independent of the load, times however much angular distortion we get per unit length of material. But that maximum shear stress, we already know to be this. So now we can combine the angular deformation with the torsional formula, the loading itself, and now we can get angular deformation as a function of the load and other geometric properties. So I think that baby there looks like it's ready to integrate. So move the dx over, integrate, everything's a constant. Those two things are constant. And everything else is also a constant. And so where dx, of course, we're integrating over the whole length of the thing. However long this piece is. And we get then that the total angular deformation is, let's see, the c's cancel on either side. We get t. This integrates just to L. And g comes down at the bottom. We get that the total angular deformation is a function of course, the load. The greater the twist, the greater the angular deformation is going to be. Also, the length of the piece. That makes pretty good sense. If you've got a real short piece and you're loading it, it's not going to twist as much. When you've got a much longer piece, it's just going to twist more. There's more flexibility in those. You can go home and test that with just a kind of a slender piece of wood. You can just grab it on the ends and twist it, grab it at different places. G, of course, being a material constant, that makes sense too. There are materials, different materials are going to twist different amounts. Steel's much different than rubber. And then, of course, J, the cross-sectional polar moment of inertia. So, as simple as that. I believe, just so you know where we are, to anchor it a little bit, that's equation 515 in the book. I'm not sure offhand if both editions that we're using here, well, including the international edition, but it's around there somewhere, just so you know where we are. So that's pretty easy to use. So we'll run a little test problem with it. So imagine some long, slender piece, maybe a drive shaft, maybe an axle or a spindle of some kind. .54 inches in length, 1.5 inches in diameter, with a load of 250 foot-pounds. And a modulus of rigidity of 11.5 times 10 to the third ASI. So we've got, what's that? That's about 4.5 feet long and about 1.5 inches in diameter. So well, probably the kind of thing you might have in your trunk that you go take into the bar fight with you. Because they're going to grab the pool cues, right, Travis? You've got this. So you're more well prepared. So we can figure out then the amount of twist in the end. Now, we'll check the units as we go along to see what happens here. 250 foot-pounds. Now, everything else is in inches, so probably that needs to be converted to feet. Inches. Times the length of the piece makes sense. The longer the piece, the greater the angular deformation. G, 11.5 times 10 to the third. and this is kilopounds per square inch. And then J, I think I have J, I don't need you to calculate it. You can confirm 0.497 inches to the fourth. So we've got pounds and pounds are going to cancel. Once you take care of the individual units, you get length squared. That's on the bottom, that comes length to the fourth. That cancels that length to the fourth. So this is unitless. Meaning then the measure of these angles are, of course, radians. So you can look at that real quick, see what we got, kind of thing we're talking about, and how much angle.
If it were foot pounds and inches, or?
Yeah, if you don't convert this feet to inches, then it's not going to combine with the other inches to cancel out. And you got to change either the kips to pounds or the pounds to kips, one way or the other.
That might be easy to forget.
Might be easy to forget. Is that what you said?
Yeah.
No, not this group. Some other, maybe at MIT or something. Those students forget this stuff, but not you guys. No, you guys know to watch your units. It's the hardest part. Sometimes, yeah, it's the hardest. I mean, this isn't difficult. You're right. It's when you get the numbers in, and we're working with some very, very big numbers and very, very small numbers. That's as hard as it is to do any of the stuff we're doing here. And don't forget, we can also find the maximum shear stress in the problem. By calculating that. Remember, I gave you that little bonus piece the other day. Once I corrected it from the board. So that's pretty easy to figure out too, and that would have units of PSI, so that's not going to take too much to work on there. Remember, torsion has the same units as moment or torque, foot-pounds, something like that. So that's going to have PSI, or KSI as the units if that's more appropriate. All right, so you run the numbers. Anybody got them yet? Joey, looking at something on your screen? No? Don't want to share it with us?
I got 28.3.
Radians?
Yeah.
Let's see, there's about 6 radians in one twist, so that's what? That's about 4 full twists around. I don't think you can even do that with one of those string cheese things. Get that to go full 4 twists, so I want to check your units here. Make sure I've got everything was right, yeah? All things to match. Somebody else got something a little different? Sounds like you may have missed the a unit, factor of 1,000. Phil?
0.0283.
Okay, that's what I have. So you have the 283, Travis. Just sounds like you missed a little bit. Now that turns out to be about 1.6 degrees, which is more than enough for there to be the possibility of trouble with gears meshing at either end of these, if that's the purpose of this as some kind of drivetrain. And the tau max should get something like 4.5 KSI. All right, so not too difficult to put those things together, but But we can certainly come up with problems that get a little bit more difficult, since the equations themselves aren't terribly so, as we said, and as Travis proved so kindly for us. It can get to be down to just a problem of watching the units. In fact, this can be very good if you think about it as a method. Oh, no, I don't have it on the board. This can be very useful as a tool to actually measure what G is in a material, as the actual testing method for determining the modulus of rigidity. Apply load on a piece of known geometry, measure its deflection, and calculate G from that, which is not unlike what we did when we found E. Apply a load, measure the deformation, and then get E from that. It's just a little bit different in the actual application of it. All right, another quick one for you. So now we have some tubular piece with a load. Actually determine the maximum torque allowable for an angle of twist of no more than 2 degrees. So limit the maximum deformation to 2 degrees. Find the torsional load that can be tolerated to stay within those limits. Okay, just a chance to work through the same thing using now some SI numbers. Remember what J is for a tubular cross-section? And you know which radius is C1 and C2 because that couldn't be a negative number. Careful. Take that. Bloodstream. Draw that it's a tube so you don't forget. Set yourself up for heartbreak. Oh, it's got you dreaming again of what were that Swiss rolls? Is that what they were?
You need to put in the modulus of rigidity.
Oh, I would, yeah. Which is 77 gigapascals. Thanks, David. Remember what the SI prefix giga means? Yeah, 10 to the 9th. Again, watch your units. We have millimeters and they're going to be to the 4th power. So that gets to be a pretty big small number. Appreciate it. A couple students are volunteering to fall for the small trap in this problem. But not everybody. Throwing themselves under the bus to protect the others. Chris, did you find a small trap? A potential one, but you lightly stepped over it. You saw what looked ahead to be quicksand. You're doing fine so far. Keep going. Got a number yet? Okay, we're looking for the applied torque. Okay, check your units. These should be in Newton meters or kilonewton meters, whatever is appropriate. I happen to have kilonewton meters. Doesn't really matter, that's 6.1, okay. Oh, something went wrong. Got something yet, David?
Yeah.
Yeah, that looks good. So Chris stepped over the trap, but didn't notice there was a pit full of vipers on the other side. Is that right, or did you just throw that in? Make me go away. Okay, all right, good. You caught. So where did you fix that? Okay, then you take it out of there. So get in the habit of fixing your own mistakes so you don't come back to them later and not notice that they're on. Phil? What's messed up? Well, you don't have the same answer as he does. Most of you are catching it now. Remember, this 2 degrees cannot go in the equation like that. It must be radians. So I think most of you caught it by now. Some started without catching it, but most of you caught it by now. 34.9 times 10 to the -3rd radians. So make sure you get that. Degrees is a unit that doesn't just disappear like radians conveniently does. It'll stay in there if you have it in there. Reconsidered? You have a loose nut on the keyboard, keypad? All right. Okay, I think most everybody's getting it now. Something like 1.83 kilonewton meters. Units should work out. Be careful on these.
What's the J?
What the actual value for that? I don't know if I have it separate. Yeah, I do 1.02 times 10 to the minus 6. And that's meters to the fourth.
So 60
Remember, these are diameters, and these are radii. I don't, why they do that, why they can't put diameters in here and then pull whatever constant's left over out to the 1/2. I'm not real sure, but it's just one of those things we like to do to students. All right, everybody catch all the little pieces in and get something like that? Not quite yet, David?
You need something went wrong in calculating J.
You're not getting that?
No.
Don't forget, these are diameters you were given. These are
Oh, the problem
radiuses,
is
radii
radii.
in the equation.
Another one to catch there.
Be very convenient if this was based on diameter, and the 1/2 to the fourth was just pulled out and added to that, but that's too nice for us to do. We're not gonna do that kind of thing for students. All right, so let's step it up a little bit. Imagine we have a long gear shaft with a couple points at which power is taken off or added by maybe some gears at certain points. And we've got a couple things going on. So we've got an applied torque at that one, an opposite direction on the other two. So maybe the center one's a drive gear, and then the other two are power takeoffs. So, and then of course the ends in some kind of bearing, just to stabilize it, of course. It's all one solid shaft, 30 millimeters in diameter. And let's see, what other little pieces do we have? Okay, let's label the different points. A, B, C, D, and E, because there's different lengths at each one, between each one. So the loads are, the applied is 450 Newton meters. Take off at B, 275. And at C, 175. And the distances between these, let's see, B to C is 500 millimeters. And C to D is 400. Now the trouble here is, well, not the trouble, but the obvious extra complication we didn't have before is between B and C, there's going to be a bit of angular deflection, deformation, and between C and D there is as well. And I want to find the maximum deflection and the total deflection. They may be different, most likely they are. Because B to C is going to twist one way, C to D is going to twist the other. So one or the other of those could be the maximum deflection, but the two together, since they'll be in opposite directions, would give a different angular deflection. So let's find the maximum shear stress and the total angular deflection. You also need two other little pieces. G is 80 megapascals, and the extra dimensions on either end to the bearings, 120 millimeters on each end. And as you can imagine, the total angular deformation will be a sum of all the other deformations along the length of the drive shaft. Okay, so we did a problem sort of like this on Monday. So for any loaded section, you need to look at what the maximum shear stress is in that section. I'll give you J so you don't have to do that. Actually, you can skip it, remember, if you use that little piece we have there. Then you don't even have to lead from the radius, you can use just the diameter is given. And then of course our usual angular deformation. You will need J for that, so I'll go ahead and give it to you so you don't have to fuss with that. Here we go. There's the solid polar moment of inertia in terms of diameter. So make it a little easier for you. 79,520. So there it is in millimeters, so you don't have to do that. What's the internal torsion in the shaft between A and B? It's what?
275.
Between A and B. You have to find the internal torsion for each one of these sections so that you can investigate which one's the maximum shear stress and which one, and how much angular deformation there is in each section, so that you can add up the total deflection end to end. So what's the torsional load A in the material A to B, the internal torsional load? What, Phil? You had an answer earlier. You're backing off?
Maybe.
Yeah, there is no load. Remember, for any of the pieces we've looked at, it's always based on equal and opposite at either end. For the section AB, there's no torsion here. It's just held by a stabilizing bearing. We assume it's a high quality one from Ace Hardware again. So in A and B, in the section A to B, there is no torsional load, meaning there won't be any shear stress and there won't be any angular deflection in that section. So it's only B to C and C to D that are loaded, because D to E is also not loaded. There's no torsion in the sections D to E for the same reason. Make sense, Joe?
What's the I?
The I just has to do with the fact there's going to be a couple sections you're going to have to figure out the angular deflection for each of the sections, because each of the sections has their own internal load and their own length. B to C is 500, C to D is 400 millimeters. So that's just an index, a summation index. Don't forget, as you calculate these, that the angular deformation in the two sections are going to be in opposite directions. So you can assign one as negative, or just pay attention to what the difference is, but the direction of the angular deflection is also important in the end, so you might do well to assign one direction as negative, one as positive. That's radians?
Yeah.
That'd be even more. You maybe have seen wrought iron stair railings where they heat the metal and then they put that real nice twist into it. Your piece would be way beyond that. It'd be more like the rubber bands on the wind-up airplanes. But at least you recognize something wasn't quite right. I'm glad you didn't put in a number like that. So check where the places are that things can go wrong. This is millimeters. This is meters. These are millimeters. This is megapascals. These are just straight newtons. So there's the places things can go wrong. All right, so as we start checking some of these. Need a torsion in the section B to C. Well, if we take off everything on the other side, well, we don't have to tip 275, so that's all the internal load is in that one. And for C to D, we can do the same thing out the opposite end. So we've got the torsional load in each. We can double check then what the maximum shear stress is. And that's d cubed because that came from a simplification of c over j, and both of them had radius terms in them. Why do I? Yeah, that's from beyond. That's this piece.
Double check.
Terry, thank you. So watching your links, let's see, B, C. I have 51.9 megapascals. Now we don't know if that's the maximum because we also need to check the other section that's loaded C to D. The shear stress does not depend upon the length of the piece. It only depends on the internal loading and the geometry of the cross section. So we get this one. Again, 16p pi d cubed. Travis, you have this one? The maximum shear stress?
33.1.
Yeah, something a little, maybe a little bit around up. Remember, the precision of these numbers isn't terribly important because you don't design to the very limit of the material's ability to withstand these loads. Put in a factor of safety of 2, 3, possibly even more. Usually, for a particular application or certainly a company standard, which I'm sure the lawyers will be happy to communicate with you when you start with the firm. Now remember that the twist is in different directions for these two sections. For one, we expect it to be that way, and for the other, we expect it to be that way. And so, we have to look at both the maximum deflection, but also the total deflection. So either one of these torsions you can sign as negative, and then when you add them together they'll cancel, but make sure you understand which is the direction, total deflection. Got something on that, Travis? Same as Chris?
I don't like it.
Probably. Not even bother to check. You guys. I don't know. For a little while, Travis, you had what, 600,000 radians?
Yeah.
Something like that?
So I was using the.
Okay, I don't know if we can cover that with a factor of safety. All right, then for each of these. And I did give you G, yep. So you have to watch out for your units. So we can call that BC. Tom, you got something? Okay. With proper units, this should be unitless because it's radians. So, Phil, you have this for BC?
I don't think it's right.
Is it 600,000 radians? Okay, then is it less than that?
Yeah.
That's what's called the Travis limit. Chris, what do you have for this first section, B to C?
2.16 instead of negative 3.
2.16 to negative 3? I have to the negative 2. 0.0216. Which do you have, Travis? That or one extra decimal? Or neither? You're less than 600,000 radians.
I'm still off that.
All right, well, let's see. The load, 275 Newton meters. The length, half a meter. G, 800 megapascals. If I have everything's in newtons and meters, that's 10 to the 6th newtons per square meter. That's Pascal, so that's a megapascal there, right? And J is in millimeters, so to get it into meters, you do 1 meter over 1,000 millimeters, but it's millimeters to the 4th, so you have to put that whole conversion factor to the 4th. So it's going to be times 10 to the minus 12th. Is that right? Or 79 times 10 to the minus 9th. Does that sound right? David, did you get that too? Okay, so now the units are all okay. Newtons, meters, meters to the 4th, meters to the 4th. And then what's that come out to be?
21.6 radians.
So 21.6 radians? Does it really?
Yeah, it's on off my
To the
back.
negative 8. Or no, I didn't change it.
That's what.
Well, let's make sure I gave you all the right numbers. Newton meters, millimeters. Gee, oh, now I can't read that.
Is it good? Negative.
Oh, yeah, sorry. Now I look at that. Good, that's the easiest one to fix. Sorry about that. Let's see. So that's what, 10 to the 9th right here. which is what we need, right? We need 3 on the bottom? Okay. Yeah, see what happens when you don't fix the little mistakes and you leave them and then find them a year later? It's still, you know, when you take this a year from now, and that same mistake will be there. So that comes out to be a little better, I hope. That comes out to be 0.0216 radians. 1, 2, 3. Yeah. Okay. And in the opposite direction, 0.0110. So maybe if we call that the positive direction, so that would make this first one negative. And then they add together to give a deflection. They cancel each other a little bit. We still get some in the negative direction, so we know that end to end there's going to be a little bit of twist in the direction of the middle torque. 106 radians, or about minus 0.6 of a degree. All right, we agree on most of those numbers. Joey, you got those now too? Now we got little pieces fixed? Okay. Not difficult equations to use. The setups aren't all that difficult, but we're watching the units, especially if I mislead you with the wrong units from the start. What you don't know is I'm obligated to do that because the equations are so simple, I have to screw you up in other ways. We talk about that at the professor meetings all the time. Okay, the next little part we need is the, well, very same type of thing we did as we were looking at the axial loadings. After we looked at the loads themselves and the stresses they induce, then we looked at the deformations they cause, then we applied what we learned there to statically indeterminate loading. Meaning, just what? What's a statically indeterminate problem? Using just the equations of statics, it's unsolvable because there are too many unknowns. For example, imagine we've got some kind of axial member between two rigid supports. So, how do you draw that? Might be easier just to put it on end, especially since what we have on this one is that it's not a constant cross-section. From one end to midway down, it's bored out. So we have a solid piece for half of it, then a tubular piece for half of it. And right down the middle is a torsional load of 90 foot-pounds. So whichever one of the drawings you prefer. Let's label this A and B are the two ends, C's the middle. And what other pieces can I give you here? We need, I don't have the radii, but I have the polar moments of inertia for you. A is C is 57.6 times 10 to the minus 3. Inches, and 42.6 times 10 to the minus 3. Now, the way we get out of the static indeterminacy of this is the fact that because it's mounted at two ends, two rigid ends, then there's no overall total deflection. Using that, we'll be able then to come up with another equation. Well, in fact, essentially that is the other equation, and we can then solve the problem. Find the reactions at the walls.
Shouldn't the J values be inches to the fourth?
Oh yeah, sorry, inches to the fourth. Okay, our statics only tells us that the reactions are nothing more than equal to the total load, but we don't know how much of the load is at each one of the supports. So we need then to add to it the deflection part, that the deflection between A and C must be equal and opposite to that between C and D. So the total deflection end to end is 0 because of the two rigid supports. So that then allows us to determine just how much is at each one of the ends. Anything missing this time? Yeah, I haven't told you what the material is. Remember what happened last time with the axial loading? The material constant, this G, in that case it was E, canceled out, but the solution is the same no matter what this material is, which I think is always very interesting. And the lengths happen to be equal, which is convenient. Well, it just makes it a little easier. When you set this up, those two will cancel. G cancels. We get just the inverse ratio of the two polar moments of inertia. Wouldn't be that simple, except the lengths are the same. Could have been too that they were different materials. That would certainly have been a possibility. But given that, you can now solve that. Now we're down to just these two equations as as enough to solve it. So it's a matter of fairly simple mathematics now. Actually, it'd be the reaction, so it'd be the torsion at A and the torsion at B due to the applied load in the middle. And they should be in the same direction. You get 51.7 foot-pounds. Now it's just a simple ratio of the two, and 38.3.
So the material doesn't matter unless it's different in each section.
Yeah, if this material is different than that material, then the G's wouldn't cancel.
But the reality is probably that, I mean, you would still treat something as having same density throughout. I mean, that's realistic.
Oh, density doesn't come into it.
Or not. However you calculate rigidity throughout the length of any given material. I mean, with the safety factor, it's enough to ignore.
Well, no, it depends on what the two materials are. If this was brass and this was rubber or something, that'd be very, very different. But it's not too big a deal, it would just be in here. You'd have GAC here and GCD, not CD, CB, sorry. CB there. Okay. Again, we have to realize what the deformation does for us in giving us the other equation. All right, questions on this one before I clear? I'm just going to set up, we don't really have a lot of time, but I'll set up another one for us that just step things up a little bit in terms of the static indeterminacy of the problems. So imagine we have a drive shaft that looks something like this. And then just to add to it, that end is hollowed out as well. So on edge looks something like that. And there's two applied loads, one here and one here of 250 Newton meters. And then some of the dimensions. The cylinder, the hollowed out section is 0.6 of a meter. Oops, not quite to scale. Let's clean it up a little bit. And then the solid part of the big shaft is 0.2 of a meter. And then 0.4 of a meter for the other part. .30 millimeter OD on the end. Twice that for the big section. And then the inside part 44 millimeter ID inside diameter. G equals 77 megapascals. And now we want to find the deflection of that free end, which we'll call A. Find the angular deflection of the end through there. Okay, and that's all the pieces.
What's the 0.3?
That's the length of this section.
Okay.
Okay, and rigidly mounted at the other end, so it's zero deflection there. All right, we only have 2 minutes or so, obviously that's the angular deflection of the intermediate pieces. And you can figure out all the pieces. Okay, so you're going to have some angular deflection in here, some here, and some here to determine the total angular deflection of that free end there. All right. Double check, see if you can get it. But I have actually 2.3 degrees as the total deflection of that end, even with each of those. Oh, sorry, double check here. These loads are not in opposite directions, they're in the same direction. Okay, so see if you can get the 2.3 for Monday, and then we'll do another statically indeterminate problem and look at stress concentrations in drive shafts.